Okay, let's go ahead and do this starting from the graph side, talking about concavity and second derivatives. Let's suppose that we have a graph that looks like this. Could you tell me where the second derivative is positive or negative, that is where it's concave up or concave down, and could you tell me where the inflection points are? And the goal is to be able to look at a graph like this and know within a couple of seconds exactly where these things are. But we'll walk you through it. So it looks like in this area I'm curving up. I know it's going down, but the concavity is up. You can always check by drawing yourself a little tangent line and saying, oh yeah, I'm staying above it. So the concavity is up. Looks like over here I'm concave down, and somewhere in here I switch to being concave up again, and I stay concave up the whole way, right? The graph stays above the tangent line the whole way, so it's curving up away from its tangent line. Great. And those points of transition, they're a little tough to eyeball, but right about there, I'd say. It switches from being concave up to concave down. And then right about here, it switches from being concave down to concave up. And that's it, right? It's when I switch from being positive to negative and then negative to positive. Those each give us points. So let's just go ahead and estimate these things and write out what we decided. So it looks like we are concave up. In other words, my second derivative is bigger than 0. I should give us a scale here to help out. We'll just go ahead and say that this is a 1 and this is a 1. So we are concave up on negative infinity, or whatever the edge of that domain is, to about negative 2. We are concave down, or in other words, the second derivative is negative on, looks like negative 2 to, I don't know, we'll call it negative a half. And then we're concave up again, so we'll tack that on to our first line. We're concave up from negative a half all the way up to infinity. Sounds pretty good. Those inflection points, we should estimate those too. And we have inflection points. And we're just going to look at the graph and kind of eyeball it. Looks like negative 2 and, I don't know, 1.25-ish. And we have another one at, we'll say it's negative a half. And the y value there is maybe minus 1.5. So minus 3/2. Always fun to have decimals in one part and a fraction in the other. So minus 1.5. So something like that, close enough. The main idea is that you understand what this looks like and you can express it in words after just seeing it in a graph. Great. Okay. Well, we have this found power. It shows up in interesting places. It turns out things like inflection points are really important in all kinds of areas to tell you when a situation is changing, but also in statistics, on a standard bell curve, the inflection point is telling you what the standard deviation is, if you've ever heard those words in stats. They show up in all kinds of neat places. So let's do an example that actually lets us find something that we already know about, which is local maxes and mins. So there's something called the second derivative test. We already learned the first derivative test. So when we go from a positive derivative to a negative derivative, we're at a local max. The question is, can our second derivative tell us that? And the answer is yes. Well, these pictures are upside down. All right, let's try this again. Right, so if we have a horizontal tangent line, kind of like in this picture here, but my second derivative is positive, so I'm concave up, well, boy, that sure looks like I'm at a local min. And in fact, it is. That's what the second derivative test tells us. And if I have a horizontal tangent line, in other words, my first derivative is 0, and my second derivative is negative, well, then I'm concave down away from that tangent line, so I must be at a local max. So my second derivative test gives us a different way of deciding if when the first derivative is 0, is it a max or a min? Just, well, yeah. Am I curving up or curving down? That'll tell you if I'm at the top of a hill or the bottom of a valley. All right, let's do an example. I think that this makes some intuitive sense. So we're just going to do one example here. Use the second derivative test to show that x squared minus 2x plus 1 has a local, that should be a minimum, not a maximum, has a local min, which I'll often just write for minimum, at x equals 1. Well, my second derivative tells us what to do. It might be nice to have a little bit of notation here, so let's call this thing f. That way I can write f prime of x is equal to, check your ability to take the derivative of a polynomial quickly, 2x minus 2. The derivative of that is my second derivative. That's just going to be a 2. Well, to use this test, I need to know when is that first derivative 0. That is saying when is 2x minus 2 equal to 0. So I have a horizontal tangent line at solving this. I get x equals 1. Cool. And now I want to know if I plug in 1 into my second derivative, what do I get? Well, it's 2. Second derivative is always 2 in this case. That's pretty nice. This is definitely bigger than 0. So by my second derivative test, I know that f has a local min at x equals 2. That's it. Great. Each of these things takes a little bit of practice. There's actually a lot of content in this section that it would be great if you didn't just kind of learn, but became intuitive in how you visualize derivatives in math. So I hope you enjoyed it.